Now, good morning friends. Today we are going to discuss about the last numerical of exercise 9.32. Now listen, learn this numerical carefully because on the same base we are going to perform the experiment to find out the refractive index of liquid. Right? That is also in our syllabus of practical. Okay. Now, it's shown in the figure. Here the equiconvex lens of refractive index 1.5. Therefore, effective index of a material of a lens, effective index of material of a lens is given. That is the Ng or the N is equal to 1.5. Right? Okay. Is placed on a layer of liquid top on the plane mirror. That is the lens, that is the liquid, and that is the plane mirror. And that is lens. So here the combination of the lens and also the liquid, that means that is the equiconvex lens is formed. Here, that is the convex lens, that is the equiconcave lens. So this combination is formed. Here we have to find out what is the effective index of a liquid. Clear this? Okay. Now, the effective index of a material of a lens is given, N is equal to 1.5, and this lens is placed on layer of a liquid on top of a plane mirror. Now, a pin with its tip on the principal axis of a lens move along the axis of a lens in such a way that its inverted image is formed. That is our object pin. Now we are observing this pin from top in this combination, and we are moving away or the moving along the axis of a lens till its inverted image is formed. The distance between the pin and lens of the liquid, the distance between pin and lens, that means with liquid, is obtained, that is the 45 centimeter. In presence of a liquid, this distance is obtained, that is the 45 centimeter. Now, the liquid is removed. In that case, this distance is obtained between the pin and lens is 30 centimeter. The distance between pin and lens in absence of liquid is obtained, that is the 30 centimeter. We have to find out the refractive index of liquid. Refractive index of liquid. And L we have to find out. Now first thing, how this combination is act. So for that purpose, that is the lens. Behind of this lens, here we place the plane mirror. That is the plane mirror. That is the lens. So as we are observing from this side, at that time what's happened? There is the plano-convex lens is act. There is the principal axis of this combination. As we place the object, so its image is obtained inside the mirror. Okay. There is the convex lens, we know that. As we place the object at its principal focus F. So what's happened? What are the coming or the incident on the lens, so its image is obtained at infinite distance, like this way. But back side of this lens is the plane mirror. So these parallel rays are reflected by the plane mirror, again incident on the lens and again focus at the principal focus. Therefore, the image of this object is obtained at the same point. Image of this object is obtained at the same point. Now, as we turn this figure like this. So there is the plane mirror, there is the convex lens, there is the pin, our object. Therefore, what is the position of a pin? So its image is also obtained at the same point. There is the principal focus. So in that case, this distance acts as a focal length. Focal length, F. Or in other words, the distance between the pin and lens is actually the principal focal length of a lens. So that is the main concept to understand this numerical or this experiment. Okay. Now after that, so what is the given here? Given data is that the effective index of material of a lens is equal to 1.5. Now the distance between the pin and lens in presence of a liquid is 45 centimeter. The distance between the lens and pin in absence of a liquid is 30 centimeter. We have to find out the effective index of a liquid. Therefore, our 45 centimeter distance is the focal length of a lens. Therefore, the focal length of a convex lens F1 is equal to 30 centimeter in absence of the liquid. The focal length of equiconvex concave lens, equiconcave with the plano-concave lens, that is F2, we have to find out. And 45 is the focal length of combination, and the focal length of combination, that is the F is equal to 45 centimeter. The resultant focal length 1 upon capital F is equal to 1 upon F1 plus 1 upon F2. 1 upon F1 plus 1 upon F2. Therefore, 1 upon F2 is equal to 1 upon F minus 1 upon F1. 1 upon F 45 minus 1 upon 30. Now 90 is the LCM. 90 is the LCM. Therefore 2 minus 3. 1 upon F2. Therefore minus 1 by 90. Therefore F2 is equal to minus 90 centimeter. Why here the focal length is negative? That is the concave lens, plano-concave lens. So thus the focal length of convex lens and focal length of plano-concave lens is now known. Right? Now we have to find out the effective index of the liquid. For that purpose, the radius of curvature is known. Therefore, we are applying the lens maker's equation for convex lens. Now, lens maker's equation for convex lens. For that purpose, 1 upon F1 is equal to N minus 1 into 1 upon I1 minus 1 upon I2. Here in absence of the liquid we are discussing, therefore N2 minus N1 upon N1. N1 is 1. That is our effective index of a medium, and N is the effective index of material of a lens. Therefore, 1 upon F1. First thing, here for convex lens R1 is equal to R and R2 is equal to minus R. R2 is equal to minus R. Therefore, 1 upon F1 is equal to N minus 1. 1 upon R minus 1 upon R. Therefore, 1 upon, what is the F1? F1 is our 30 is equal to N 1.5 minus 1. Here 2 upon, so there is the 3 by 2 minus 1, that is the 0.5 into 2 upon R, 1 by 30. Therefore, 1 by 30 is equal to 1 by 2 into 2 upon R, 2 cancel. Therefore, R is equal to 30 centimeter. R is equal to 30 centimeter. That means here the given length is equiconvex. Therefore, the areas of curvature of both curvature surface are same. That is the 30 centimeter. Now the effective index of a liquid. For that purpose, here we are using now Lensmaker's equation. For concave lens, so the plano-concave lens, concave lens, 1 upon F2 is equal to NL minus 1 into 1 upon R1 minus 1 upon R2. Now listen, here the plano-concave lens. So one surface is the radius of curvature is infinite and R1 is minus R. Here R1 is equal to minus R and R2 is equal to infinite. Therefore, 1 upon minus 90, because the F2 already we obtained, there is a minus 90, is equal to NL minus 1. Here 1 upon R, there is the minus, there is the minus 1 upon R, minus 1 upon infinite. So this minus cancel. Therefore, 1 upon 90 is equal to NL minus 1 into 1 upon R. R already we obtained, there is the 30. There is the 30. Therefore, 1 by 90 is equal to NL minus 1 by 30. Therefore, 1 by 3 is equal to NL minus 1. Therefore, NL is equal to 1 plus 1 by 3. So 1 plus 0.333. So 1.33. That is the effective index of liquid. That is the effective index of liquid. Here, where is it? Only we have to apply the Lensmaker's equation separately for the impedance of liquid. That means there is for in absence of liquid, there is convex lens, and in presence of a liquid, that means for concave lens. So by using the first equation of the combination of the lenses, we find out the focal length of the convex and concave. Already the resultant focal length is given, or the focal length of a combination is given. So keep in mind this numerical, because the same experiment we have to perform. Clear? Okay. Okay, now good morning friends. Last numerical 9.32 is the last numerical of our exercise. That means we completed the chapter 9. But the most of the students in commented on that the 9.11 they not understand very well. For that purpose, again we are repeating the numerical 9.11. Right? Now listen carefully. What is given in question? A compound microscope is consists of an objective of focal length is 2 centimeter, and that means the focal length of objective FO is 2 centimeter. There is the compound microscope is given, and focal length of eyepiece 6.25 centimeter. Focal length of eyepiece FE is given 6.25 centimeter. Now the separation between these two lenses, separation between objective and eyepiece is given, D is given as 15 centimeter. Now, where the object is placed on the objective to obtain its final image at first at the near point distance, that means the D is equal to 25 centimeter, and second is at infinite distance, and also find the magnification or the magnifying power in above both cases. Again, a compound microscope with the objective of focal length 2 centimeter and eyepiece with focal length 6.25 centimeter. The separation between the objective and eyepiece is given, there is a 15 centimeter. So at which point or at which position the object from the objective should be placed to obtain the final image at first at near point distance D is equal to 25 centimeter and second at infinite distance. It means we have to find out the position of the object or the object distance. We have to find out object distance U from objective U0. Clear this in both cases. The near point distance D, near point distance D is equal to 25 centimeter. Okay. Before starting our discussion, first we clear about that. What is the situation in compound microscope? There is the objective, eyepiece is larger. The separation between these two distances is D. Now, whatever the image formed by the objective is obtained near to the principal focus of eyepiece. So the image of this object is formed at very close to the principal focus of the eyepiece. That is the FE. And that is the FO. Or in other words, image obtained by the objective, that is our V0 distance, that means the image distance for objective. Now, this image is act as a virtual object for eyepiece. So that is act as a U. Now we have to find out this position U0. We require this. Now, the image formed by the eyepiece first is at near point distance here. That means that D is equal to 25 centimeter. So D is minus. Actually, there is a V. So now V given UE, we have to obtain by taking the V is equal to 25 centimeter. So first image, final image formed at first at near point distance, Therefore, image distance D becomes the image distance for eyepiece V is equal to minus 25 centimeter and FE is equal to 6.25 centimeter. So from lens formula for eyepiece 1 upon FE is equal to minus 1 upon UE plus 1 upon V. Now we require the UE. Therefore, take the 1 upon UE in this side. Therefore, 1 upon V minus 1 upon FE. VE minus 25. So minus 1 upon 25 minus 1 upon 6.25. 25 is the LCM. Therefore, minus 1 minus 4. Therefore, minus 5 upon 25. So it's equal to minus 1 upon 5. There is the U 1 upon UE. Therefore, UE is equal to minus 5 centimeter. So thus we obtain the object distance for the eyepiece. But distance between object and eyepiece, for the objective and eyepiece, is 15 centimeter. Therefore, object distance for, image distance for objective, that is the VO, is equal to 15 minus 5 is equal to 10 centimeter. Is 10 centimeter. Now we are applying lens formula for objective, and therefore the lens formula for objective 1 upon F0 is equal to minus 1 upon U0 plus 1 upon V0. Therefore, 1 upon U0 is equal to 1 upon V0 minus 1 upon F0. Now, already we obtained the V0 is 10 centimeter. So 1 by 10. And focal length of the object is given 2 centimeter. 2 centimeter. Therefore, LCM is 10. So 1 minus 5. 1 minus 5. So it's equal to minus 4 by 10. Therefore, U0 is equal to minus 2.5 centimeter. So that is the distance of the object from the objective to obtain the final image at near point distance D. Now, what is the magnification? The magnifying power. Magnifying power is M is equal to MO into ME. MO, V0 upon U0 into ME. Here the image is formed at near point distance, therefore the magnification is 1 plus D upon FE. 1 plus D upon FE. Now, V0 upon U0. V0 is 10, U0 2.5. Now 1 plus D, 25, FE 6.25. 6.25. Therefore, there is 4. Here 1 plus 4. Therefore, 20. Thus, the magnification M is equal to 20. So, there is the first case when the image is formed at near point distance. Right? Now, second part, if the image is formed at infinite distance, the same manner, first for the eyepiece, find out the UE. This UE is obtained. On the base of the UE, we can find out the image distance for the objective V0 again. Again, apply the lens formula for objective, find out the U0. And also find out the magnifying power. Okay, now in B part, if the image is, final image is formed at, now, infinite distance, at infinite distance. Infinite distance, that means there is the image distance for the eyepiece. Therefore, image distance for eyepiece Fe is equal to V is equal to infinite. Now from length equation for eyepiece 1 upon Fa is equal to minus 1 upon UE plus 1 upon V. We require the UE. Therefore 1 upon UE is equal to 1 upon V minus 1 upon Fe. V is infinite. 1 upon infinite minus 1 upon Fe. Therefore, UE is equal to minus Fe is equal to minus 6.25 centimeter. But distance between objective and eyepiece is 15 centimeter. Therefore, image distance for objective, that is the V0 is equal to 15 minus 6.25. It means the 8.75 centimeter, that is the image distance for the objective. Again, we are using the length equation for objective. Now, length equation for objective 1 upon FO is equal to minus 1 upon UO plus 1 upon VO. We require the value of UO, therefore 1 upon UO is equal to 1 upon V0 minus 1 upon FO. V0, U0 are known. U0 first. V0 8.75. So it's equal to 1 upon 8.75 minus 2. Minus 1 by 2 because the FO is equal to 2 centimeter is given. Therefore, 2 minus 8.75 upon, here 2 into 8.75, 17.5. Therefore, we obtain the U0 is equal to minus 2.59 centimeter. So thus the image, the distance of the object from the objective is obtained, that is the 2.59 centimeter. And magnification, when the image is formatted in finite distance, so magnification M is equal to magnification by the objective into magnification by the eyepiece. For objective, ratio of the V0 upon U0 into D upon F. V0, already we obtained 8.75. V0 2.59. D 25, that is the 6.25. So it's equal to 13.5 is the resultant magnification in that case. That means the final image is formatted in finite distance. Clear this? So that is our B part if the image is formatted in finite distance. Okay.